want to go to Mars, which is cool. Mars is definitely a fun place to go, with Venus coming in second now that we think there might be life in the atmosphere there, which, yeah, we haven't sent stuff to Venus, so it'd be cool to go there. But this is an opinion poll. No one really wants to go to Mercury or the moon. They're not as exciting, I guess. Not hospitable to life, probably, so that's fair. But luckily, some people are interested in the outer planets, which we'll get to talk about today. Okay. So I wanted to start just by finishing up. We were talking about Mars last class and why we don't think there is water there anymore. And so I threw up this graph and I just wanted to talk about it a little bit more. So this is a phase diagram for water. So when we think about phases of a material, we usually think solid, liquid, or gas. And that's true, but it's not quite that simple. There are different phases of the solids as well. So if we think of water, how ice and snow are different, they're both solid water, but they're different phases of solid water. And I think I kind of threw this out there, but if anyone's a Vonnegut fan and has read Cat's Cradle, they talk about Ice 9, the ninth phase of ice. It won't destroy the world, luckily, but there is a ninth phase of ice. So if that's a little bit of like sci-fi trivia for folks. And what we can look at is that we know, based on the temperature and pressure of a planet, we can figure out what phase water will be in. And we know that Mars has a temperature range of about 15 to 300 Kelvin, so, or 150, sorry, to 300 Kelvin. So kind of in this range, we're in here, but the pressure stays right around 700 pascals. It doesn't have much of an atmosphere, so the pressure's pretty low, and it stays around 700 pascals, which is kind of down here. And so that means that we stay in this range where water is always going to either be in a solid state in this blue area or in a gas state in this orange area. So even if there used to be water on Mars, if it had more of an atmosphere, so maybe the pressures were a bit higher and there was atmosphere on Mars, it no longer has an atmosphere that can sustain water. And we know that based on this pressure diagram for water and the conditions on Mars. Now, it's possible that there's some form of life on Mars that has been able to survive without water, that we just don't know what it looks like. We haven't found anything yet. It doesn't mean it's not there. And that's something that I think is always, when we talk about sending humans to Mars, there's this issue of we don't want to contaminate Mars with our own bacteria. So whenever we send a probe to Mars, we can like heat it to thousands of degrees and kill any bacteria that might be on it, but you can't do that with humans. So there's this issue of when we send humans to Mars, or if we send humans to Mars, how do we make sure we don't accidentally bring our own bacteria and measure that as a form of life on Mars? So I think that's always kind of funky to think about. Because yeah, you can't heat humans to thousands of degrees without killing them, unfortunately. That being said, even though there's no water that we think of, there is some very briny, very salty water, like seawater on Mars. Not much. Most of it does either evaporate or solidify, but we have seen some flowing intermittently on the surface of Mars, specifically in shadowed spots of craters and canyons. The reason briny water can exist is because salt water has a different freezing temperature. When you add, like if you think of putting salt out on ice to make, or on sidewalks in the winter to get rid of ice, it's because that the salt water will be liquid at lower temperatures than non-salty water. So there is some very, very, very salty water on Mars that is in a liquid phase, but there is not much, and it is only there intermittently. So it's not a good place for life to exist because it's not always there. So you need kind of a safe environment that sticks around. This water does not seem to stick around. So there is, my caveat to there being no water on Mars is there is a teeny bit of salty water that comes and goes. the last thing I want to end with on our terrestrial planets and Mars is that Mars has 2 moons. So Mars is the only terrestrial planet besides Earth that has moons, but they are much smaller than our moon comparatively. So Mars has Phobos and Deimos. Phobos and Deimos are both pretty small, 12 and 22 kilometers across, and I like to call them like potato moons because I think they look kind of like potatoes, since they're oddly shaped, not nice and spherical like our moon. The other thing that's kind of interesting is that Phobos is doomed. So Phobos is small enough and it's close enough to Mars that it's actually going to be pulled apart and crash into Mars eventually. So it's not in a sustainable orbit. It will eventually crash into Mars and become part of Mars, and Mars will only have 1 moon. We think that both Phobos and Deimos are captured asteroids. So they're small enough that, and Mars is closer to the asteroid belt, so at some point maybe some smaller asteroids got close enough to Mars that Mars was able to gravitationally hold on to them and they became moons of Mars instead of nearby asteroids. So that's kind of our terrestrial planets. We had Mercury, Venus, and Mars, and as well as the Earth and the Moon, which we covered pretty well. And we kind of played around with how we can use geological techniques like we do on Earth on the other planets by looking at cross-cutting of surface features as well as craters to try to age the surfaces. So those are kind of the big things I want you to take away from this section. And we will move on to the outer planets, unless I will pause for questions here. Does anyone have questions about Mars or terrestrial planets in general? Okay, well, feel free if you think of something to throw it in the chat. I do have that open, so hopefully I will see it. And let's move on to the gas and slush giants. I think your book calls it the gas and ice giants. I think slush is funner, but either way. So these are the giant planets in the outer parts of our solar system. So there's 4 of them that we are going to talk about. There's 4 of them, period, sorry. Jupiter, Saturn, Uranus, and Neptune. They are all much bigger than Earth, so this is kind of not scale model separated, but scale model in terms of size. And we can see that Earth is very small compared to the other, the 4 outer planets. We're also going to split these up into 2 categories, our gas giants, which are going to be Jupiter and Saturn, and our slush giants, which are going to be Neptune and Uranus. So we're going to start with the gas giants and then move on to the slush giants. So Saturn and Jupiter are gas giants. They are, like I said, much, 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 much bigger than the terrestrial planets. Jupiter is actually more massive than all of the other planets in our solar system combined. So if you had a scale and you put Jupiter on one side and all the rest of the planets on the other, it would be pretty close to balance. Jupiter would be slightly heavier. So Jupiter's around 300 times as massive as the Earth. And its core of Jupiter is the core of Jupiter is about 10 to 50 times the mass of the Earth. So even just the center core part of Jupiter is more massive than the Earth. But that's a pretty big range. You might notice 10 to 50 times that's a wide range of possible masses for this core of Jupiter. And that's because we don't really know a ton about what's happening inside of these gas giants. Same with the slush giants. With the terrestrial planets, we could use Earth kind of as a model to think about what was happening inside of them. With these outer planets, they are nothing like us, so we can't really use Earth as a model. They're completely different. They are mostly gaseous, which is not what's going on here, and we haven't been able to send a ton of probes to these outer planets because they are so far away. So recently, 2016, Juno got to Jupiter, and Juno was only the 2nd spacecraft really to orbit Jupiter after Galileo. And it took 5 years to get from Earth to Jupiter. So sending a probe to Jupiter takes about 5 years. And there's only certain equipment that's going to work on that. We can't send things into the atmosphere very well because they'll burn up as they fall in. And so it's hard to really think about what's happening inside, but we have a pretty good idea what's going on based on, or we have some idea, I should say, based on the orbital spacecraft that we have sent to these 2 planets. We can also, if we think I've had 2 people who have attempted the Saturn composition lab, and we can do some things just by looking at the density of Saturn, by density of these planets, sorry, I should say. We can figure out the density of these planets from Earth on a whole, and we can use that to at least put some limits on what they might be made out of. And so that helps us build this idea of what the different layers might look like. We can also just use different forms of observations to figure out what's happening inside of these planets. And one of the things that has done by looking at these planets in the infrared and radio has told us that both Jupiter and Saturn are hotter than we would expect for the distance they are from the sun. So if they were just absorbing sunlight and re-emitting it, we would expect them to be a lower temperature than what we see. And what that means is that they both have an internal heat source. So there's something inside of both Jupiter and Saturn that is causing them to warm up. And we think that is from material collapsing onto the core. So Jupiter and Saturn are still kind of finishing their formation. Heavier material is falling through the layers into the core. So the heaviest material will be on that rocky ice core in the center. And as that stuff falls down, it causes things to heat up because falling is motion, and we can kind of think of temperature as motion. So falling, as they fall, they lose gravitational energy and they gain kinetic energy, which is radiated away as thermal energy when they hit the center. So throwing a teensy bit of conservation of energy at you, but the main idea is because they are still collapsing, as material collapses, you heat things up, and that needs to be radiated away. All 4 outer planets have this occurring, so all of them have some form of internal heat source from this collapsing, but the heat sources in Jupiter and Saturn are larger than in Uranus and Neptune. Mostly because they're bigger, so there's more stuff to collapse. So another thing I'll throw in here is that sometimes you'll hear people say that there's, oh gosh, I think it's diamond rain on Saturn. And this is kind of what they're talking about. They're talking about the heavier material on Saturn raining down onto the core, but it's not going to be like diamonds. There's not a surface you could stand on and grab some diamonds out of the air. It would be just carbons and other heavier materials falling onto the core. So this is just some basic information about Jupiter and Saturn. Both of them are mostly hydrogen and helium, because hydrogen and helium are the most prevalent elements in our universe. We will talk about this more when we get into the Big Bang much later in the semester. They both have pretty small densities, so less than rock at 1.3 grams per centimeter cubed. Water has a density of 1 gram per centimeter cubed, so Saturn is actually less dense than water. So if you had a really big bathtub filled with water and you could put Saturn in it, it would float, which is weird to think about. Of course, we don't have something that big, so can't do that. But all the other planets would sink, Saturn would float. They're both much bigger than Earth. So Jupiter's radius is about 11 times Earth's radius, whereas Saturn is closer to 9.5. Jupiter is about 300 times as massive as Earth, while Saturn is about 100 times as massive as Earth. So their material they're made out of is less dense, but there's so much more of it that they are more massive. We can talk, surface gravity is a little funky to talk about on these planets because we don't they don't exactly have a surface that we are sure of. We think the core might be solid, but we don't completely understand what it would look like. So whether or not you could walk on these planets anywhere, it's hard to say. So when we talk about surface gravity, it's a little funky to think about, but Jupiter's is slightly higher than Earth's, whereas Saturn's pretty close to Earth. Jupiter doesn't have much of a tilt at all, which tells us it won't really have seasons at all, whereas Saturn has some amount of axial tilt, which tells us that it'll have seasons that might be similar to Earth's, except they will take longer because a year on Saturn is much longer since it is further out in the solar system. Neither of them are very eccentric, and then both of them have pretty short days. So that's something that's kind of interesting. Even though they're much larger than Earth, they are spinning much faster. So a day takes about half the time as a day on Earth. So one rotation on Jupiter is about 10 hours, where on one rotation on Saturn is about 10 and a half. And that's going to affect the crazy weather and atmosphere that we see on both Jupiter and Saturn. So this is just a time-lapse image of the atmosphere of Jupiter kind of spread out, and we can see that there's white, oh gosh, it's bands and the word is escaping me. I think it's on the next slide. Yeah, so brown belts and white bands, that's what it is, sorry. So the brown areas are called belts, the white areas are called bands, and they are similar to the Hadley cells on Earth. So Earth had those areas where the atmosphere heats up and then cools down, and you get kind of these rotational cells. The same thing is happening on Jupiter and Saturn, just there are more cells. So Earth has 3, Jupiter has quite a few. We can see kind of as the winds change direction in the brown belts and the white bands. The reddish brown belts are warmer and slightly lower in the atmosphere. The white bands are higher and slightly colder. So they're made, and the colors are caused by the composition. So the white zones are made of ammonia gases and ices, so mostly water and ammonia gas and ices that have risen and frozen and become clouds, whereas the reddish brown belts are from hydrocarbons, so hydrogen and carbon molecules bound together with some potential phosphorus and other elements in those brown bands. They're lower, they're drier, and they lack ammonia and water ices. We get this mostly from their colors. I also said we can look, that's the way we know the heights of these zones and the temperatures is by looking in the infrared. So anything that has a temperature glows in the infrared. Next section, we will talk more about the different kinds of light, so we'll get into this more, but we all glow in the infrared because we have temperature. Anything that is warm will glow in the infrared. So we can use those temperatures of the belts, the infrared brightness, to determine the temperature of the bands and the belts, and we can figure out that the brown belts are warmer and the white zones are colder, which also gives us an indication that they are probably higher out in the atmosphere, further from that internal heat source. This is just a fun thing. Like I said, Juno got to Jupiter in 2016, so we're getting a lot more information about what's happening. And one of the things they did was take a bunch of pictures that were part of a citizen science project that people looked at to look for fun things. And one of the things they found was Jovi McJoveface, so they thought this looked like a face on Jupiter. Some of the storms. Okay, so we've talked a little bit about the different bands on Jupiter. Now I want to investigate the storms, and this is going to be an activity for you. We're going to look into how fast winds are moving in the Great Red Spot on Jupiter. So this is the kind of big storm that we know has been happening on Jupiter since at least 1840, quite possibly since the 1600s. We've been able to observe this storm. So very, very old sustained storm, and we're going to look to see how fast the winds are moving in this storm and compare that to Earth. So this is going to be your day 7 activity. So if you go here to your assignments on day 7, there's something called storms on Jupiter. And this one should all work. And the idea is that we're going to use kind of a scale to find the size of this storm and then some time-lapse images to figure out how quickly it's rotating. And just a little note on this, if you had a paper copy, we could use rulers, but what I did when I measured the size is I kind of made my own little ruler on a piece of paper where I got the diameter of Earth and I compared that to the size of the red spot. So that's your measuring stick is essentially Earth, and we're going to use that to try to find the semi-major and the semi-minor axis of this ellipse that is the Great Red Spot. Just a little reminder, semi-major is going to be the long axis but split in two. So the major axis would be all the way across. The semi-major axis is half of that. The semi-minor is going to be then this axis, doing our best to measure that. And then again, half of that semi-mean.